currently the time thing.
Okay, let me share my screen first. Okay, can you guys see my screen?
Yeah, not
Yeah,
full screen, but
you can make it full screen.
the data.
Is it looking good now?
Yeah,
Okay. So in our previous work, we already know that we already knew that you might see the EBSD data and the interface layer has extended after we doped with some materials, right? Actually, the morphology has been changed. And then I've recently I was studying the eutectic alloy, the morphology, and I find these papers is about some some if you give some they call the trace element into the eutectic alloy. Actually, you might change the morphology of the two. I mean, these should be two compositions. And in this picture, you might see in the figure A, it's aluminum and the silicon eutectic alloy. And then the white one, the white region is the aluminum, and the black region is the silicon. So if you give some trace elements, here they give them like calcium or magnesium into the materials. It's almost like a 50 to 200 ppm, and then you might see the morphology of the silicon has already changed. It's most similar. It's almost similar like when we doped with the cadmium telluride into our samples, or maybe co-doped samples here. And then with the concentration of the trace elements increases, actually the morphology also changed accordingly. And then here, we might introduce a concept here is the entropy of the fusion of the sample. So actually the entropy of the fusion is defined by the delta HF, which means the fusion of an enthalpy, or maybe we can also see it's a the latent heat of fusion. And this number can be both measured using the DSC or calculated in the phase diagram. And for this entropy of a fusion, if you get a smaller number, then probably it means that it's grow faster when during the crystallization process. And like for the typical metal, the number should be typically lower than 2. But for a semiconductor, it typically should be larger than or maybe around 10 such number. And so here, if we go back to the last slide, and you might see in this aluminum and the silicon eutectic alloy, and you can see that the this aluminum is always look like coarse. I mean, it's said coarse, but I couldn't really see from this BSE pictures. But since silicon is a semiconductor, so and the entropy of the entropy of fusion is quite large, so it's more like a smooth. And here, so if we look at the phase diagram of a silver antimatter, and then we might see that if we cool down from the 112 compositions and from the liquid phase to the solidification, solidification point. And actually, here in this regime, this light cyan regime, there should be a liquid plus the silver 1 minus X, antimony 1 plus X, and tellurium 2 plus X. This combination should be the leading phase, which means that it forms in the liquid first. Then you might have the silver rich combination in your liquid. Then the formation of the tellurides can be facilitated and surrounded by your grains of the let's see, the silver non-stoichiometrical silver antimony telluride phase. I think this actually, since our previous work is a quench-based sample, I mean, more or less is a quench, and it's not like a very slow cooling. So, compared to the slow cooling sample, it's more non-equilibrium solidification process. Okay, so you can see this picture that if you cool down your sample in the non-equilibrium solidification process, actually your phase diagram of the lines of the liquid phase and your liquid phase and your solid phase can be really elongated if you use some non-equilibrium strategy to synthesize it, and your sample tended to form such like layer by layer and they compress with each other, rather than if you use a equilibrium phase formed, like it's almost a single
Can
grain.
you zoom into this picture?
Which one?
Here. What is the picture on the bottom? What is the x-axis? WB and WO.
The weight per percentage.
Weight of the concentration of B.
Yeah.
So that's a binary alloy. So you have temperature in the Y and you have A on the left and B on the right. So it's the classical binary systems.
Yeah. So actually, you might see the left one is the equilibrium solidification process, and the right one is the non-equilibrium solidification process. And actually, there might some if you cool down your sample in the non-equilibrium solidification process, then the component segregation happens inside of your matrix. So you might see that it's actually you might see from the center from the center outwards, you might see the different combination of your alpha 2, alpha 3, alpha 4, which they might be the same phase, but I mean different combination.
Sorry, alpha 2, alpha 3, alpha 4 is like, how do you read that? It's just the alpha phase.
Yes.
Phase here.
Yes.
Right?
Yes.
Liquid
Yeah, a different combination.
But when you mean different composition, I can't picture it.
Ag2TE, Ag2.1, TE 0.9, Ag2 2.2, like TE 2.3, like that, like different compositions of Ag2TE.
Yeah, because for a certain phase, actually your composition of your we said AXBY, right? So it's a range rather than a single composition. Like the X can be changed from 0 to 0.1, but your Y can change from 0.9 to 1, and all of this region is show the alpha phase.
Got it.
Yes.
But Chen Guang, so for
So
this
at T2,
one, it's
go ahead.
oh sorry, but Chen Guang, but for this is for equilibrium synthesis, right? It's not DJS, right? The picture you showed.
I mean, the left one is the equilibrium synthesis. The right one is the non-equilibrium synthesis. It's like a quench, something like that.
Is that the picture that they use for steel?
Can
Yeah,
be.
typically for eutectic alloys.
Yeah, okay. Yeah, it rings a
Yeah.
bell. I was like, wait, where have I seen this? I
Yeah,
remember that.
eutectic alloy.
Yeah. Yeah. So actually Jeff Snyder has a paper on this. Let me find it for you.
Mm-hmm.
So yes, you're right, by the way. You're absolutely
Okay.
correct in what you're saying.
The nucleation of these alpha sites is heterogeneous, like this. At T2, T1 is the liquidus. At
Yes.
T2 on the right-hand side, you have
Hmm.
heterogeneous nucleation of the alpha phase. It's correct? It should be, right?
Yeah, should be.
Like by
I
heterogeneous.
mean, the formation of the alpha 2 actually is also dependent on many things.
Mhm,
So it's just a schematic here.
mhm.
Yeah.
Mhm. If it's like a hadrite or the dendrite, it's
Okay.
really depends on a lot of things.
But here, this picture is simpler because you only have a single phase. It's just a concentration of that phase compared to the liquidus line. But what you have is multiple phases which nucleate with different formation enthalpies
Yes,
and hence different entropy of fusion.
yes, and which is very hard to measure because in the 112, actually your silver telluride is always the formation of your silver telluride is always energetically variable.
It's favorable unless it's doping suppressed, right? So it's
Doping
favorable in the
suppressed.
baseline
I
compound,
mean,
right?
yeah,
That's what
the
you mean.
point is here is that if you're looking at the if you are looking at this phase
Yeah.
diagram, right?
Yeah.
Actually, you need to control that your leading phase
Ah,
to be as much as close to 112 first, instead of you surprise your silver teller use your
yeah.
silver telluride first.
Yeah, yeah, yeah. Yeah. Sorry.
I
Yeah.
mean,
I understand. Yeah.
yeah, I mean the results could be the same, but the logic is a little bit different because because in the liquid, if you solidify your sample from the melting status to
Mm-hmm.
the
Yeah.
solid,
Yeah.
then actually the first phase formed is the silver antimaterialite, is not
Yeah.
a silver telluride.
Okay, so I have a question on this entropy of fusion.
Mm-hmm.
Tm is the melting temperature?
Yes, TM is the melting
Why is
temperature,
that
the
fixed?
solidification temperature.
The solid, what temperature is it on the diagram here?
It's here if you see the TM should be this line, this green line. I mean the liquid
Okay,
to the other this line.
to the solid phase, the
Yes.
liquid line.
Yeah.
Okay, so you're basically normalizing everything with respect to the liquidus line. So does Tm fixed for all the phases here? Like antimatter telluride has the same Tm, Ag2T has the same Tm, or is the Tm different?
TEM.
Tm.
I mean, it could be
TM.
different.
Oh,
Then-
TM. Okay. So for the silver telluride, if you see the whole, I mean if you see actually the TM can be changed with the different composition of your silver telluride and the silver telluride and your antimony telluride. So this is only part of that, right? It's from from 30% to the 60%. So
Okay.
actually, it can be changed.
So is this
They
Tm?
show something like
So
a
Tm for this value is here, and Tm for this value is here, and Tm for this value is here. Is this correct?
Yeah.
yes, yes.
Okay.
So so you need to fix your composition. Then you start to cool down from a certain temperature to to your solid.
So in this intermediate range where you have two phases, the cubic Ag to T
Yeah.
and let's say the alpha, I don't remember alpha, the beta phase of AGST, AG, the ternary phase, right?
Mm-hmm.
So the Tm is fixed for both those phases, even if it's Ag to T or it's AGSBT too.
No, here is a solid phase actually.
No, but there's the Tm fix.
Yeah, you need to. I mean, if you have a.
If I have a point here,
Yeah.
do I normalize with respect to just this single Tm here?
If you cool down
Yeah.
your temperature from
At this composition.
here and to here,
Yeah.
so I think you need to calculate your composition from this line.
Mm-hmm.
Yeah. I mean, there might be something here, but you need to touch to the other one. So your composition should be here, and this is your silver antimetallaride, and the other and to some points rightward should be your silver telluride, something
Okay.
like that.
And you normalize with respect to the same TM.
Yeah.
And the delta HF is the, I see it says entropy, but we're not considering.
Yeah,
This is just the
typically it's
formation
for
entropy.
the homogeneous matrix instead of the. I mean, if you have a mixed phase, then probably it doesn't work. So here, like if we calculate this number, we need to measure the pure silver antimetallaride, which is like for this one, if we use the 112 phase, like let's say if we fix the 112 phase, then here we need to use the silver 0.9, antimony 1.1, tellurium 2.1, and then the silver telluride.
So how do you measure this?
Well, that's a problem. You might find some data on the silver telluride. Let's see, this is the silver telluride.
Can we run Monte Carlo simulations for this? Kedar?
Actually, I have no idea on this.
I
But
mean,
for the silver telluride, there are some papers on measuring it. This should be the 8 cal per gram. I mean, because it's a single phase, but there is no record on the silver antimetallaride.
Yeah, so what I was thinking is how much does the small change in stoichiometry, because you're going quite far in the composition, right? This is, I mean, still close to 112, right?
Yes.
So really what you're changing is, if you think about how the solid is being formed, right? So you have a lattice which is determining the phase. The atoms are in their fixed positions, right? So the formation of those bonds for the perfectly crystalline structure should be well captured by a calculation of formation energy.
Yeah.
Okay, then what will change is the configurational entropy, which typically for a ternary compound is not so bad. Like it's an order of magnitude lower. Okay, there's some papers that show this. So let me put some numbers to this. I think this is what you should do next, to start to put some numbers to this. Like you have 8 cal per gram. I don't know what that is in terms of, I'm more used to EV per atom, okay, by looking at the number of moles and stuff. So you can do a similar calculation based on the density of that Ag to Te, convert to the number of moles, calorie to EV, and you should be able to get a number, right? So my estimation would be that the change in the formation energy for a ternary compound from the ordered to the disordered is not much. So you can start with the ordered AgSbT2 as a good approximation of delta HF. Okay, this would be my assumption.
Or if possible, we can use like I mean, if there are some I think for the non-stoichiometrical silver antimetallaride, the enthalpy of the entropy of fusion is quite similar as the antimetallaride, because if you
that's what I'm saying.
Yes, because if you look back to some papers about if there are a lot of antimony and tellurium rich regime, like a silver which we said silver deficient samples, and you might see that it's the antimetallaride and the silver antimetallaride, it shows the lamella structure. It has, this one is a AST, but this one is a ST, right? It shows the lamella structure. So I mean, in the grain growth, and if your entropy of your fusion are quite similar for both of your composition, then you are mostly like to get this kind of parallel lamella structure, because the growth speed are almost the same.
Yeah, so I mean, I agree. So what you would do is, let's start with some first order approximations. This is really nice, right? And you would test the limits of whether this works or not. Like the experiment that comes to my mind is that since you have captured the microstructure with EBSD,
Yeah.
right? So you should be able to then calculate the ratios of the different phases,
Mm-hmm.
and then you know the entropy of fusion with some approximation for each of the phases. And then you should be able to map it out on the phase diagram, what your kinetic route is to get to some endpoint, right?
Mm-hmm. Yeah.
I think that'll be really nice.
Okay.
So
Mm.
I
last,
think
Yeah.
another thing that you might wish to do is, since you have the TM and the STM, and there's a lot of areas, so you
Yeah.
can see the numbers, right? So based
Yeah.
on check the paper I sent in the group chat, because I use that paper to write our paper, right?
Okay.
And then you can compare the analysis that Jeff did in that paper,
Mm-hmm.
looking at the composition of the liquidus, and map it onto this, right? And also, like, I don't know if this is true or not, but like, can you write the enthalpy of a non-stoichiometric compound as the weighted sum of the stoichiometric one? So like Ag 1.1 Sb1 T2 can be like X times the enthalpy of Sb2 T3 plus Y, the enthalpy of Ag2T. Because if that's possible,
Maybe.
Maybe.
if that's possible, right? I remember this because I wrote it in one of the versions of our paper. Like, if you're looking to go look into the 23 versions that we have,
Uh-huh.
at some point there is an
Uh-huh.
analysis of the STM and the liquidus and the different compositions
Uh-huh.
based on the paper that like Jeff Snyder published in Acta Materialia, right?
Yeah.
And you can use that. You can use that analysis to map it onto your own analysis.
Yeah.
Sorry, I'm just curious, why you're
Yeah.
saying STEM? Why not EBSD?
STM has a lower, has a finer spot, right? So in the TM, you have areas where you have captured very, very well what is the composition of everything. Whereas EBSD, if you think about it, right, EBSD is still EDS. The composition is arbitrary. What you capture in EDS is structure. Those points are Kikuchi patterns. They are not composition, right? We have composition data, but it's not very reliable. So that's why I think that doing it
Which
in the
STM data are you referring to? Are you referring to like the
supplementary figures 13 to 19, I think it is. So some of the data, do you have our paper handy, Chengguang?
okay, I think I know what you're talking about. Yeah,
I
can you
think-
put the pictures? Let's
Yeah, I
find
think Chengguang has them. Like, if not, I can do
what
it as well.
Zainul used to
Yeah, exactly. So he has tables,
locate
right?
the grains and stuff. Yeah, the table.
Yes, he has tables.
Yeah.
And okay, it's still EDS, but like, at least we know what area he mapped,
Yeah,
right?
that's
So
perfect. You already have
I
the
would-
data actually.
Yeah, we have the data, and I had done some of the analysis, and I think someone didn't like it a lot, so they made me remove it from the paper, so we never actually included it. So,
Mhm.
but like the idea is simple. Like, you just take the analysis that Jeff Snyder did and map it onto what we have.
Mm-hmm.
Like, that's what I did. Like, that was the idea. It's simple, like, it's not super hard, and it can complement your analysis as well.
Mm-hmm.
And then, like, I think it might be worth looking into whether we can write the enthalpy of a non-stoichiometric compound as the composition, as the weighted sum, right?
Mhm.
I don't
Uh-huh.
know. I don't know if that's very accurate or not, but it could give you numbers for enthalpy of non-stoichiometric compounds based on tabulated data.
I'll try.
Yeah.
Mm-hmm.
So if you put up the pictures so that everybody can see them, I can tell you what numbers like I think can be useful for you.
Yeah, our supplementary information, right?
Yeah, exactly. Yeah.
Let me stop sharing and
Yeah, thanks.
share again.
Because sure, it's still EDS, right? So it's not super accurate, right? Like, because it's not being calibrated on whatnot. Stop. So you see that table? You see that figure D?
Mm-hmm.
So for instance, the area 6, area 7, area 1, area 4, area 3, those are like single areas, right? Obviously,
Yeah.
disregard whatever is mixed, whatever is in the middle. That's no good, right? Forget about that. Can you go to the next figure, please? That has this data. Okay, stop. See? And there you also have so that area 3, area 2, area 1, all of that, right?
Yeah.
All of that can be like data that you can use because you have, like, I think it's trustworthy, and of course, like, be careful with the dopants because the dopants will move the energy, right?
Yeah.
So, but like, I think this is data that you can use, and you should, honestly.
Yeah.
Yeah.
But I mean, you cannot quantify. This particular depends on the area.
What do you mean you cannot quantify?
I mean the ratios. Like if you go
What
with
ratios?
if you go with the different census routes, and suppose
What?
say
Okay.
you want to quantify how much
Yeah.
the percentage of AG2TE formations.
Right.
I mean, even the same sample, if you
Yeah.
different areas, different compositions.
Right.
So
That's why he cannot take all the areas. And actually, if you look into it, like that's normalized by percentage, by atomic percentage. So even though,
I
yes,
agree. I think if you were able to do this on a few areas, take some statistical data, you should be able to separate them. There will be
Yeah.
an error bar. You should be
Yeah.
able to separate the kinetic route from the thermodynamic route. Why do you say you can't
no, I
quantify?
think Mahesh is talking about quantifying how much AG2TE there is based on the EDS data,
No,
which is not the
no, it's
point of the exercise. The point of the exercise is to quantify the composition of the solidus to map it to the liquidus. That's
I
it,
think
right?
the point is just to
maybe
show that you would have a thermodynamic route, which is the slow cooling.
Yeah.
And as you change the cooling rate with some error bar, you're just able to map out different regions in the phase space. That's it.
Yeah.
And then that's that you're controlling the microstructure is at the end of the day is the result of this entropy of fusion being different. That's fundamentally what you're saying. And so by changing the cooling rates, if you go towards the thermodynamic limit, you should go towards the thermodynamic limit, and then you can show different cooling rates can actually give you different structure. I'm sure this has been done before. And there'll be an error bar, of course, right? Because there'll be variability. But the error bar is just a bar, so it's fine. As long as it's separable, it's okay.
Make a caveat, just mention that this is all EDS and therefore it's not like absolute numbers, but like you can compare within your own samples, right? Which is the point, I think.
Yeah, if different stoichiometry is, I mean, not quantifying the amounts.
Yeah, this is not, but this is elemental. We want to have phase.
Yeah, if it is stoichiometric phases to identify it differently, yes.
This is why I thought EBSG was
Yeah,
better.
yeah.
Giving you different elements, right? But I think there's also some analysis later, right? Which one it is. Can you go down? I don't remember now. But we know it's not just cadmium, it's cadmium telluride, right?
Yeah.
Isn't it true?
Both.
Where is the picture where we do that? Because this is STEM EDAX. We don't want STEM EDAX. We want not just elemental composition, but we should be able to show the phases.
Up. Keep going. I'll tell you to stop. See, this is the advantage of writing your own things. You know where things are. Go. Keep going. Stop.
It should be here, right?
Yeah.
How is this done? This is EBSD.
This is EBSD.
Yeah. So you need the phase fractions.
Yeah.
The STEM will not give phase fractions.
But the
Really
phase
elemental
fraction will not give you the off stoichiometry. So like it will give you 112 always, because that's the CIF file that we used, right?
Yeah, but I mean there is a physics angle to explain that, right? Like I said, you would say the ordered 112 phase is basically where the bonds are formed and results in the structure. And the additional removal of atoms in with removal of cations, anions, etc., is basically should be an error bar. So you can I mean, this theory is never perfect. So it's reasonable to say we start with the ordered AGSBT2, or I think what Ivan mentioned, which I think Cheng Wang himself said, is that if you have DSC data in literature, you don't even have to do it yourself, because you would have to do it yourself at that particular point, right? Which may be tricky. So instead, you just look for literature data, which has DSC for HF values, and use that as a starting point. Let's first see if it gets you somewhere, right? I don't think you need to go crazy on, is it accurate? Let's first see if you're able to separate your thermodynamic cooling rate from your fastest rapid cooling rate, and see if you're able to map it out. I think that's already pretty good.
Yeah.
The only issue is you don't have EBSD at multiple points, right? So if you go back to your presentation, you only have EBSD at room temperature.
But yeah.
So XRD, you should actually use XRD to do this, right? Because presumably, even though you don't see the H2TE phase, I don't know if you do. I mean, I realize it's just a broad hump, right? That's the problem. The minority fraction doesn't show up on the XRD. But I mean, Jayanta's work, for instance, the competing phase, you could see it in XRD. When you do in situ XRD, function of temperature, that's how you get the different phase fractions, right? So like what I'm trying to say is you overlap it, right? Basically, Yeah, you want to basically get multiple points along these lines. Am I
Yeah,
right?
yeah.
And then just show that there's difference. But to get multiple points, you need to be able to map the phase fraction at different temperatures.
I can do that with the in situ XRD here.
Except, my question is the AG2T doesn't show up in the XRD, right?
It does, right? I mean, in the
Okay.
I mean, if you meld it under this solid and liquid diagram, this solid and liquid line, probably it won't show in the XRD. But if
I mean,
if
that
you
is the thermodynamic cooling. You know, what you would have to do is how do you get data for the kinetic cooling?
uh
Yeah, sorry, I didn't collect the data cooling down, but I can do the measurement heating and cooling. And then we can see when we cool down, because we know that the temperature at which we melt, right? So we can start
Yeah.
cooling down from there, and then we can see what phases appear first. That we can
Yeah.
do. I can do it here.
Yeah. Like basically you can generate the top curve here. You should be able to generate the top curve here. Right? The question is, how do we generate the bottom curve? Isn't it? Because we need to then essentially, you only have one point, which is this last point. You see, this is the room temperature. Unless you stop the reaction at a higher temperature, which you cannot do, right? This is the problem. You see what I mean? Like you're basically going from a melt and you do a slow cooling, whatever cooling rate rapid you're reading, you're going straight to room temperature.
Yeah.
So of course, there are different phase fractions, which then results in a certain microstructure.
Yeah.
But we don't have intermediate points, right? How do you measure the intermediate points is my question. How do you know the phase fractions in the intermediate points? Am I right? This is my understanding of the...
I think we can only can we not do it with in situ XRD as well though? Can we not prepare individual samples? So like vary the x-axis and then do the in situ heating at different temperatures, targeting that and looking into the... we can generate both curves, right? So this one over here, so this one over here is heating. So you start with the precursors and you start heating and you collect spectra and you do that for different composition ratios. So you have different points in X that map to different points in T, and you get the phase fractions from in situ. And then
how are you changing the X?
We can, right?
No, this is the... Isn't the point here is that you're starting at one point in this composition space. You're only in one point in the composition space. And then the different weight fractions, what forms is a result of the reaction. You can't control it.
Can't we quench the sample at different temperature here? Like you make 4 or 5 sample and just directly quench from T2 to room temperature, T3 to room temperature.
Yes, that's possible because we don't go all the way to T melt.
Yes, you go like T3, T4, T2 and then just quickly cool it down instead of going to average T1.
Yeah.
I mean, didn't we do that for the paper actually? Like 5 seconds, 20 seconds.
No, the temperature, not the time. It's the temperature.
Time and temperature are related, right?
Time, yeah. The heating curve, right?
But the time and the temperature are related. The longer the time, the higher the temperature, because temperature increases continuously.
Yeah.
So by cutting it at different times, you cut it at different temperatures.
Yep.
No?
Okay.
I mean, that's my experience, at least.
I think, Ivan, you cannot do a fast XRD. No XRD is fast enough as Joule heating.
Yes.
That's the point, right? You cannot do an NCD XRD.
But you don't need but you don't need the whole pattern. You don't need the whole pattern. You need selected peaks. You need peaks of interest, right?
You just need certain points.
Yeah, exactly. So you don't need to collect from 10 to 90. You need to collect from 20 to 23. It's 3 degrees.
Yeah, exactly. Yeah.
You don't need the whole pattern.
You just need to collect these points, a few points of
Yeah.
temperature, and
Yeah.
you just measure with XRD. So I think it could be that, right? I'm just trying to get the idea that is this T equivalent to the temperature of reaction? But it's different, right? Now you see the reaction proceeds by going to the melt and then cooling, and so there are
Cooling.
intermediate temperatures along that range. It is not the same
cool.
as heating only until T1 because that's different. You see the problem?
Yeah. Is it cooling data or the warming curve actually?
Cooling. This is cooling.
Cooling, then okay.
In equilibrium, there will be cooling and heating will be the same. In non-equilibrium, for sure, they will not be, right?
Then yeah, different temperature XRD will work actually.
No, how do you
Yeah.
cool it so?
Huh?
You
can stabilize the temperature, right? At that temperature in high temperature XRD.
That's
We have
thermodynamic. How do you compare the rapid Joule heating?
the rapid one. Yes, you
The
cannot.
whole idea here is that the green is rapid Joule heating, right?
Rapid Joule heating, yes.
And then the cooling rate is much faster.
Yeah.
This is rapid Joule heating, which is the rapid cooling rate, and then this is the slow cooling rate, which is the thermodynamics.
I mean,
How
you
about
you need to have a different quenching temperature, quenching rates at the XRD stage.
You literally need to freeze your reaction at those
yes,
intermediate
yes, or
when
just
you're cooling. How do you do that?
one more idea. Is it we can do the band gap will change here at different positions here when you do this?
Man,
What
band gap
changes, sorry?
measurements in this material are very hard. Band gap.
No
Because
band
you
gap.
No, I don't like the idea of the band gap, man.
No, yeah.
Not that I don't like it, it's that I don't think it's gonna work.
For this material won't work.
Yeah.
the fast
I don't
measurement
know.
you need, right? That position.
Yeah, so currently we can't do it. We can do the thermodynamic experiment, but we need to be creative. Like, how would you measure the intermediate? I don't know.
Pictures, optical image.
You need to
So-
have an RGS inside a beamline.
So can I ask a question? So how fast you guys are looking at about the cooling?
Very fast.
Few second, I think.
2 Celsius
So-
per minute or 10 Celsius per minute.
2 Celsius per minute. I mean, a lot of the in situ cooling XRD is about this range, right? The heating and cooling rate per peg, is it?
2 Celsius is very slow.
Very
Normal.
slow.
Yeah,
Yeah.
2 Celsius degrees is very slow. Even 10 Celsius per minute is slow in
Yeah.
situ
So you
XRD,
can't-
right?
You
Am I
can do
correct
X.
in that, Chengwang? What is your cooling rate, Chengwang?
Hello?
2 Celsius per minute, 5 Celsius per minute, and 10 Celsius per minute, and the natural cooling.
Yeah, Haiwen, I
well-
think you're right. The problem is that like in this sort of samples, you would be looking into like yeah, so okay, got it. So the power, please muted yourself, mate. So I think the problem would be the broadening of the peaks. So when I was in IMRI doing these experiments, it was very hard because you would be using it, your beam wouldn't be, your peaks would be very broad. Your peaks would be omega broad. And when it comes to the convoluting, like it's very hard because your peaks are so broad that there are multiple solutions to the same spectra. And to be honest, all of them are equally good. So you cannot really tell.
You cannot you cannot tell the phase fraction from the AST to the AG to T, right?
Yeah. So normally because and it makes sense, right? In situ XRD, because it's thought, in single crystal XRD, because it's thought of for single crystals, your intensities are your phase fractions. So it makes sense to do. It makes sense to do. So basically, a poly refinement in a single crystal is a Rydberg refinement.
Yes.
Right. So then you don't care about the broadening of the peaks. You don't care. But like if you have multiple phases and so on, then it becomes really, really hard to solve.
Is there
I
any
tried.
possibility of like a characteristic AST peak that just very far away from edge to T? No.
Yes, but like the antimony telluride peaks are overlapping.
Oh shit.
You can go ahead and look at our paper. I think like supplementary figure 4 or something like that has some antimony telluride peaks, and you can see how they are really, really close. And that's for powder XRD. So powder XRD means polycrystalline
Understood.
materials, and you still have the resolution to separate them. You can see them, right? But like, can I? Okay, so let me.
You
Well,
want to
anyway,
share
whatever.
something?
Like the peaks in single crystal XRD, if you don't have a single crystal, are very broad. Yeah.
One more queries here. What's the rate here? The temperature rate from alpha 2 to alpha 3 going down. You have any idea slope values here? Then we can decide based on that. Like, is it very fast or is very the slopes values here?
All control, like they are different slopes.
Yeah, but if you get to know the
In
slope
this
values,
curve, Chengwang, the question is, in this curve, do you know what the cooling rates were?
yes,
In
from alpha 2 to alpha 3, alpha 3 to alpha 4, what's the
which
rate?
one?
Yeah, the red and green, do you know what
Yes.
the cooling rates are?
No, it's just I mean, there is no absolute equilibrium solidification process, right? So
And
it's just a comparison. Like I mean, if you have
But
a very
this
slow
is,
cooling, then you show the left picture. Then you have a very fast cooling, then you show the right picture.
but then you
You
no,
will
cannot.
but
never get the, I mean, absolute equilibrium process
has
during
anybody done this sort of experiment is the question.
well,
Have
I
you
think
seen any evidence, even in the reference that Pepe has sent or others, have they done any, has there been any evidence for cooling rate controlling the phase fractions? Like martensitic steel versus regular steel. There must be, right? And how do they do it is the question.
I think a rough drawing could be possible. Yeah, I think
Okay.
it could be possible. But if we want to get a very accurate number, then probably not.
No, not accurate number, but just to show that the microstructure and phase evolution is different. I'm sure
Yeah.
people have done that, where they
I
try to
can
control.
fix the 112 theoretical telluride from the melting states.
You're missing the question, Chengwang. I'm asking, can you look at steel, iron with carbon or iron with some silicon?
Yes.
And
Yeah.
depending on the cooling rate. So martensitic steel is really fast cooling. They quench it.
Yeah.
And it becomes very hard. Right? So if you just check in literature for martensitic steel versus some other steel, I don't know what the steel is.
Yep.
Different steel grade. Maybe people have studied this evolution of phase as a function of the cooling rate. How do they do that? Maybe we can get some idea on how they do it.
Yeah, I can.
Yeah.
I think this is a very I mean, for the stainless steel, the techniques are I mean, all the theory are very are mature than
Yeah,
theoretical
exactly.
telluride. And the next slide is about the if we only look at the pure silver atom halide from the quenching status in our previous experiment, one might see that there are a lot of like silver telluride precipitate inside our matrix, right? Sometimes it shows very elongated, and sometimes it might be show the starting formation of the dendrite. And so actually during the quenching process, we also need to face some challenges in the latent heat of the fusion and the low
Sorry,
thermal
what are
conductivity.
these diagrams? What composition? What is this?
This is
This is
112.
from the paper. This
Yeah.
is this is from the paper.
Yes,
And this is
this is our
no
previous paper.
no doping.
No doping.
Okay.
This is you see the small silver telluride precipitate, nanoprecipitate inside this matrix. And these formations the formation of the thermotelluride here might be dominated by the low thermal conductivity and also latent heat fusion, means that during the solidification process, actually inside of your materials, the latent heat released, but the low thermal conductivity of a material itself. So even though you get the solid surround your sample, but inside of that is still maybe sometimes it's still in the melting point or above the melting point, or became the solid first. Then after the latent heat released, then it's go back to the melting point. Go to the melting status again and resolidification. But I think this problem is very hard to solve in these materials, but I just want to I just want to propose here. But probably if we change I mean, I didn't get the EBSD data and I didn't get the TEM lambda right now, so probably I'll check it later if we change the cooling rate, if the morphology of the precipitate changed.
Yeah, so as an update, I think Chengwang, you're getting trained on the Talos here in IMRI, right?
Yeah. Mm-hmm.
That's one. And when is that going to get done?
I think there are some documental process need to be done.
Okay. But you're
first.
trained already.
Yes. I mean, the problem is not the TEM. The problem is that the sample preparation. Currently in Singapore, we don't have a proper precision ion polishing system to polish our sample.
So you said you're going to send it out, right? Have you sent it
Yes,
out?
I'll send out this by this Wednesday.
Okay. So let's see how that works.
Yeah.
And then the EBSD, we had a chat with Coral and Dennis.
Yeah, so we passed the sample last week.
Excellent. So they are
And,
going to do a lot of things. They're happy
yeah.
to collaborate.
And also I passed a sample for LFA last week. So everything is in process. Everything is going.
Yeah. Yeah, so this is ongoing work, but I think you just need to, the only thing you need to look at is solid fraction or fraction of different phases as a function of cooling rate. There must be people that studied something. It might require some funky tool. I don't know. Okay. So Haiwan's question, you cannot do it in XRD because the XRD sample stage cooling rate is fast, but you have a thermal mass from your sample. Okay. You cannot suck that much heat out of grams of sample. Powder may be okay, right? So if you want to look at powder, maybe that's possible, not a pellet. So if you think, I mean, I don't know if you have a fast XRD. Who has a fast XRD? I don't know if anybody has a fast. What is the fastest cooling rate in the XRD in A lab, Pepe?
So if you do it in air, it's pretty fast. I think because you basically have it open in the chamber. So it would be like close to air quenching. But normally we do the experiments here in nitrogen, and then the cooling rate is much slower. But there can be a way for us to make it faster, I think. Of course, then temperature control and so on kind of goes through the window. But if we just care about fast, maybe we can do it. I'd be open to try if you guys want me to, honestly.
Yeah.
Try.
I've been measuring your samples every now and then, but yeah.
So the key question is that there's two problems now. If you think about it, one problem is how is AGSBT2's phase evolution done as a function of cooling rate? It has nothing to do with DJS, right? And then you check in literature if people have studied this, right? I don't know if maybe you didn't find anything, Chengwang?
Not now, but I'll check it later.
Yeah, check it carefully. Okay, it's good to know because everybody knows this is a complicated phase. Everyone knows Ag2T precipitates. It's been going on for so many decades. So somebody must have looked at this sort of entropy of fusion, the concepts that you're introducing, and then compare the phase fractions, show the difference in cooling rates. If I had to bet smart money, I would bet people have done it. So the bigger problem would have been salt, which is what we're talking about, the easy experiment. That's what I would guess. Some XRD cooling rate in nitrogen versus air, whatever, other ways of doing it. But DJS is intrinsically different, right? Supposedly. It's like much faster because we get to the melt faster and cool it really fast. I don't know, right? So there, I think I haven't heard any idea as to how can we freeze a particular phase, take a snapshot. That's a tricky one, right? Unless you do a DJS inside a beamline, which we can explore. For example, but it requires a special holder, right? Now, people have other special holders where they do in situ heating and cooling in the beamline. We can talk to them. I think
They are
Pepe
not.
had one in Australia, I remember.
Yeah, I know those stages. They're not suitable for us.
Mhm.
I
So
mean,
they
whether
have a name. They have a name. Let me look it up for you, Kedar.
it's like we
Okay,
need to check the requirements of the space, something. You can directly put our DGS itself, like our space occupation. I mean, we don't occupy much space, right? So,
yeah.
Have you been to a beamline?
I mean, not the beamline, XRD, especially XRD stage. So the XRD heating stage is much smaller, bigger than our DGS setup. So even if you do some kind of workshop, like some jig design, you can do our DGS setup exactly at the XRD stage.
In principle, I agree. In practice, I don't think we have access to the
Any one of our own
I mean,
XRD.
it's all user controlled, right? In IMRI, we don't have a good user there anymore,
Mm.
right? XRD and
Uh,
Chengwang and
could
TU is a big.
could we Linkum stage? You might heard about the Linkum stage, right? Chingwang, could you check the heating rates in Linkum stage?
Yeah, that's the one that I used in Australia. It's not good for us.
Okay.
Lincoln. Oh man, thank you so much. I was looking for the papers.
Lincoln stage. Before
Yeah.
last time
Link.
I checked.
Yeah, it's
But I
really
mean,
good, but it's not very good for us.
as soon as you use if you use the DJS setup in XRD, I agree, you're getting what you need.
Yeah.
If you use Linkum stage, my bet is that someone has done it before. You see what I mean? Unless the AGS problem is not solved for whatever reason. I don't know. Maybe it's not that interesting. Maybe people haven't looked at it. I don't know. That's possible, right?
I feel it's like feasible to do DJS in XRD stage if some flexibility of getting XRD mission.
Mahesh, then let me ask you the question. If you feel, are you willing to talk to the XRD super user in IMRI where they put the DJS inside?
I mean, if PIC is kind of okay, we know it's not dangerous, so then can.
Who is it? Who is the PIC now?
I mean, now saying, I mean, Lipons, I will check with what is the? There's two ladies, one lady and I
Yeah,
forget the name.
some girl there, I think.
Yeah,
Now,
you can make a very small DJS reactor.
I
We
trained
have
her SPS, so I can talk to her. Yeah.
Yeah, just talk to her. And basically our electrical connections we can do externally.
Yeah.
You just need to put it in, but it's not easy because you have a circular
height. Yeah, I know. I got it.
height and then,
I think I thought about it. Yeah.
yeah.
Still,
So
if you move our DGS setup 1 centimeter up and down, like kind of where the X-ray incident surface is equal to our material. It's fine.
Ladies and gentlemen, welcome to the
Who's that? Who's that?
this is a bit I will send on
Okay.
something.
Yeah, it's fine. Okay, yeah. I will check also. It's very nice. It's not only for this setup, it's good.
Yeah. So I think there's two to address. I think the idea is good, but
Yeah.
Chengwang, we should check first what is done in AGSBT to literature. If they study different cooling rates with different tools, what are the tools?
Yeah.
And then how is the DGS different? Then we try to do something. And you can think about a creative problem of how do we freeze the phases at particular temperatures. Right? I think that's really the question. What do you mean by the pulse frequency, Christine? Can you elaborate? Which pulse frequency? Christine's asking, can we control the pulse frequency?
I think the Delvin's tool, we can control the pulse of the current and control the cooling rates.
Yeah. But so I think it's possible. But for Chengwang, I think he's starting on a simple problem where just maybe that's how you control the cooling rate already.
Mhm.
How do you control the cooling rate? Is it by doing pulsing?
Uh, control the cooling rate right now.
I think it's by current control, right? Like so you
Yes.
vary the current, like you pass enough current to like lower the temperature. So like current
Right.
like decreases linearly or like non-monotonically. I think it's
So
current
the
control.
pulsing is
Yes.
not done. So we can look into it. Sorry, Delvin?
No, it's exactly what Pepe said. Yeah. So you apply just a small enough current so that it doesn't cool too fast, but not
Yeah.
enough to heat it up.
It's the clever way to do it. Well done, man.
I don't think there are many papers working on the cooling rate of the silver antimetallaride, but as far as I know, because almost all the people, I mean, not almost, it's all the people that they use the traditional solid state synthesis, right? It's the film sitting in the tube and they put it in the furnace and then they cool down. And actually, the cooling rate of the furnace is very hard to control. So I think there are many researchers working on the decomposition mechanism of the silver antimetallaride, right? Because thermodynamically speaking, the silver antimetallaride is unstable and easy to be decomposed to the many phases. And that might be so many people interested in, but not many people working on the cooling rate because they cannot control it using the traditional furnace.
So anyway, this is going to be part of your thesis. Cheng Wang, you should do a good literature review to see what is the state of the art in AGSBTE2. Okay.
Mhm.
You have that anyway for your thesis.
I mean, this is a different scenario with like a stainless steel because for the stainless steel actually people can operate it in the air. Right? Whatever the cost or just uh burn it in the furnace or in the pot. You just take it out and then pour everything in the water or in the cold oil. Then so the actually the cooling rate can be easily more easier than the like a flame sealing
But for
technique.
you to fill this theory, it's
Mm-hmm.
not just are you able to cool it fast or not.
Mm-hmm.
The question is, are you able to detect the phases for different cool as a function of the cooling rate?
Yeah. Uh, I
That's
mean,
what you need to read. So you would read this iron or aluminum literature on metal alloys
mhm,
and see what is the techniques, and then see have people use any of these techniques for AGSBT2. That's what you need to do. Right? That's your background research.
mhm,
I think this is a good idea, Haiwan. Like I thought I was thinking of this as well. Just cold oil or liquid nitrogen. Maybe you can actually freeze the phase because you just lock it. There's no diffusion.
mhm,
So really at different points in the cooling rate, the way you get T1, T2, T3 is you like the reaction is not fully complete. You drop it, drop it, drop it. I think it's possible.
I actually tried that with germanium telluride to see if I could freeze the cubic phase. It didn't work for me. So maybe it works for AG2T, like
Yeah, but I mean,
something is
you're
too
not trying
hard.
to freeze out a particular. There, you had a different goal, right? You're trying to see if the cubic phase is stabilized. Here, you're not trying. You're just saying you're observing. So the snapshot of the phase at different temperatures. Hopefully, this thing can lock it. And that, I mean, if there's evidence that people have done it, then maybe that's the right way to do it. I like
Yeah,
this idea.
you're right. Yep, good point. Yep.
I mean, dropping from the furnace or dropping from the DGS setup?
DJS.
I
DJ
mean,
setup.
not easy.
Yeah, well, I didn't electrocute myself, so it's good.
I mean, from DGS, like need to take out. Yeah, can. Right.
From DJS.
Because you need to unload and you need to take out the quadge choke from the thing. If it is furnace, just open and from the temperature and drop. I mean, you can try how fast you can unload from the DGS at that high temperature.
I think they've tried it before. So, it's like.
Oh, nice. I didn't know.
You don't need I think you need 3 points to make a curve, right?
Mm.
So, you don't need to do it like 10 different points. You just take your cooling rate and then okay, in 10 cents, 10 cents per minute or something, you know, you have enough time. Within a minute, you can unload. I think it's possible.
Mm-hmm.
You need something creative like this. Okay, otherwise there's no differentiator. So please help Cheng Wang out, guys, on this because he needs it for his next paper, and that's sort of the last paper in his thesis. Okay.
Yeah,
Uh,
that's great.
maybe a quick update from Delvin and Christine on the sample synthesis. Anything you want to update? But I think we've already been chatting separately, so if you just want to say a couple of words, that's fine. And Pepe.
For sample preparation, I think we only left 4 samples to frequency mill and hand it over to Sonia.
Great.
Probably happen on Thursday, so we can
Mhm.
finish finish everything first 14 samples by this week's meeting.
Great. We have a meeting this week, right? Thursday.
Yes.
Okay, perfect. So we'll chat about the availability of this. Please try to prepare some sort of presentation where we summarize all the results so we can start from there and discuss with the team. And
Okay.
Pepe, are you preparing the figures? Like, I think it'll be good to have the figures on Thursday for the paper.
Yeah.
Okay. Please spend some time on it so that we can get the initial figure draft ready.
Yeah, I had a call with Amol and Somia last week, and we talked about Amol has a really nice idea about the structure of the paper. So yeah, basically I need to find some time to work on the figures, and I will send you the report soon, actually, Kedar.
Yeah, the
It's on
report
my,
just
it's on my mind. It's just that Gerd still hasn't gone to New York, so we're having lots of discussions about some stuff here. So sorry,
yeah.
I haven't done it before. Sorry.
Don't spend like more than half an hour or an hour on it, as long as you can find something. Just summarize it, put it in the form of a report. 1 page, 2 page. Yeah,
Do you
no
need
big deal.
figures?
Yeah, I mean the figures like from WhatsApp. You don't need to make any new figures. Whatever you have,
Okay.
just
Okay.
put it in. Nobody cares. No one's going to read the technical details.
I don't know. I'd rather do it well than not.
Okay, I won't complain. All right, one or two figures is sufficient. Okay. Who wants to go next? Jayanta, anything you want to update?
Yeah.
I went after that.
So actually, I try to prepare the different copper composition. So actually,
Doping.
yes.
Mhm.
So initially at like 414, so there is like 15% of copper telluride. Then when I added 2%, then it will got phase pure. Then in case of copper 4.2, so this is also few other phases there. And after adding 2%, so there is few small peak, but I have not quantified how much it is. Here actually, here 4.2, this two.
Sorry, can you walk us through this? You have, let me see, the base compound is at the bottom left,
Yeah. So actually, yeah.
right?
So here actually I vary the copper concentration with the titanium concentration. So like at 2%, so it is almost phasable, but few like phases, like few impurities there.
Okay.
So this is actually I prepare for small scale to checking the XRD. So for the transport one, so should I proceed with this 2% titanium addition? But there is like few other phases also. So it will does not too much effect on the transport, right?
Hard to say. Very hard to say. I think the 2%. So let me see one second. This is pure phase, right?
Yes.
And then when you start to introduce extra copper, you start to form these extra peaks, the
Yes.
star.
Yes.
And do you know what they are?
Mm, maybe so I not confirm, but maybe some copper telluride binary phase. But I have to check actually. Yeah,
Yeah.
I'll check.
And the sample, this is powder, and this is carbothymol.
Yes, covered.
Is the color different?
No, almost same.
Almost the same.
Yeah.
Is it shiny? Does it look shiny or is it like black?
It's shiny actually. Little.
That's good. So, and even after this, it's still shiny, right?
Yes, yes.
Okay. What happened to the idea of doing some optical experiment to look at doping or something? Is there, have we thought about this? I think we were going to chat with Mahesh Pawan about this, right?
Yes, so I think FTIR can help, but for that, actually, I need to prepare a phase pure of all the sample. Like,
Why?
so otherwise, so if there is some impurity in the extra copper, so it may be deviate, right, from the ideal one.
I think optical measurement will come from the bulk matrix. So with minority phases, I don't think your optical will change so much. I think that's a reasonable assumption. And what you're really looking to check is there some feature in the FTIR? Like, in organic polymers, we've been doing this for a while, like the polaron peak at low energies tells you whether they're delocalized or not. Similarly, there should be some feature, right, in FTIR, Pawan, that should tell you if it's doping, de-doping, or something is changing.
On FTR. FTR.
FTIR, yeah. Written FTIR kada.
So with FTIR, can you tell if it's doping or de-doping? What is the signature we look for?
We're just checking band gap actually. Band gap
Oh.
is changing a bit, but doping,
Because
I'm
the organic polymers, we saw the polarons, right?
yes, V to the polygon. That is totally different feature.
Right.
Mhm.
Quick question, but these are metals, right? How are you going to measure
Yeah,
the band gap of a metal?
it's not
Non-metallic.
metal,
No, actually, these have like narrow band gap. So around like below 0.4.
but even below 0.4 should still be semiconductor.
Yeah, it's semiconducting. And presumably the Fermi level is in the band. And so the idea was to de-dope it.
Yes, so somehow but even that case, you'll still see metallic nature or semiconducting nature.
I mean, the easiest is what about the SPS? Right? Where is the SPS right now?
Here, this guy, Andy, is visiting at 11:30
Okay.
and with online with Japanese guy.
Okay.
Don't believe that email. He's like a crazy guy. I don't want to make any fuss, so I just agree.
Of course.
Yeah.
I see.
So actually for the transport property measurement, so actually I need only change the copper concentration. So if I like change the titanium one, then it will be difficult to say like for which concentration changing it will coming.
Yeah.
So I
I
think
think
then
with 2% titanium, because you know it's phase pure in the base compound.
yes.
The appearance of the impurity phase doesn't change. And I mean, you will always look at look at the AGSBT2, it's the best example, right? We always have AG2TE, but the transport you can do dope and de-dope, no problem.
Okay. Yeah. Then I think I'll prepare the bulk and then I can do the measurement also.
Other thing, can you try tellurium with selenium and sulfur? That might also will be.
Yes, yeah. I'll try.
And we wanted to do it, but for this paper, we want to get it out.
Yes,
So
yes.
essentially, the reason we can't get it out is because Andy is still working on the theory. He's
Yes.
prioritized theory. So once we know the theory, we can just write, oh, this is the band gap of the material. Everything else is done. He stabilized a phase at 310 Kelvin that has not been done before, and phase pure samples have been made. So that itself is the paper. But while we're waiting for that to happen, I asked Jayanta to do doping, de-doping with copper vacancy because it's easy to do.
Yes, easy to
Perhaps
do.
it's the same with selenium or sulfur. I don't disagree with that. But there's some evidence for the semi-metallic samples with copper vacancies, you should be able to de-dope it, which is why he's going to lower, like, 3.85, 3.9.
Yes.
It's good that you have the other side as well. And I think if you have copper telluride phases forming, then there should be less copper in the matrix. So that means you should have more copper vacancies anyway. So maybe it's a good, so then I'm hoping that this is a quick and dirty way. Maybe the CBAC will increase and we'll start to see some thermodynamic performance.
Yeah, just check with the handheld system. Is it a CBEC can change or not?
No, but there's no pellet. It's
Uh,
powder.
Still powder form. Okay.
I mean,
You
you
can
can compact.
cold press
Cold
the files and just check the CBEC. No need to bother about
Okay.
conduct.
Yeah.
You can
But
cold.
actually, these samples, Jayanta, DJS, these are cover thermal,
Cover
but you're
them.
going to proceed with DJS, right?
Yeah, I will
Okay.
proceed. So I'll just making in small scale. So I don't
Yeah.
want to waste a large sample. So that's
Sure.
all.
I think you can proceed with 2%. I
Mm,
think clearly it's working. Like the majority phase is still
Mm.
there, right? And then most of the peaks look quite similar. So I think the presence of small impurity phases is not a problem in thermoelectrics.
yep.
And what you can do is do DJS
Mm.
with a small reactor. And like I think power, I forgot. Like with power and what power might just use the handheld meter and as a
Yes.
function of for copper doping,
Yes.
just
You
measure
should
let's see what
CBEC
data you
actually.
get.
Yes.
So we look
Just
at the
cold.
trend of
Just cold press the powder. Actually, this should be enough.
no need to cold press because this DJS is like
Oh, direct
already
solid
pelletized.
already. Yeah.
There's
DJS.
some voids inside, but it doesn't matter. Right?
Yeah, it doesn't matter
Okay.
actually. Mm.
And also plot the resistance. Just I know
Yes.
that
Resist.
resistivity is
Yes.
different.
Just metal
You cannot
resistance.
do resistivity because you don't know the geometry, but do the resistance.
Okay. Okay.
Just plot to see what you get.
Okay.
This kind of work will help Cheng Wang as well, because I think when Amit and Cheng Wang they start, we're going to do some exploration of machine learning. If the simple handheld, measurement is sufficient, that's a good screening tool at room temperature. I mean, anyway, something to think about.
Do you have without 2% of titanium? Do you have the copper vacancy? How the sample looks like? The XRD?
Yes. This.
Mm.
So these are
No, there is with copper 4. There is a
Yeah.
copper 3.85, right? The beam.
Yeah.
Do you have the parent compound without?
Okay. No. But
try.
yeah, I can try. But I think there should be some impurity or more impurity. But I can try. Yeah.
Yeah.
And sir, so this like variation of this copper thing. So this should be go in this paper, right? This is in this paper also.
Yeah, it should. I think.
Okay.
I think it'll add some value
Okay.
while we wait for theory to come in. If you're able to dedope, then you show that you have control, right? Some thermoelectric properties would be nice. But of course, let's see what. So do keep pushing Andy, okay? Don't wait for him to respond for 3 weeks. You should just like work him every week, man. Like my paper is being held up. What's happening? Okay.
Yeah.
All right.
And actually, I need few feedback from you guys about my figure. I don't think this is like super good, but so this is actually my first figure. So in this figure, so in first, actually, I'm talking about this carbothermal one. Then in the second figure B, actually, so actually I quench at different temperature, and I like told the story how the phase evolution is happening. Then talking about the extra titanium will give me like phase pure compound. Then I talking about for the large scale, I using the DJ synthesis. So
my is it's a bit confusing because you have two different synthesis parts, right?
Yes.
Hard to say, but yeah, I mean, you can work on the figures, make sure it's pretty. Now, the other thing that is not clear from this is that the 2% titanium is already phase pure, right?
Yes.
So you need to sort of emphasize that as well somehow. But here, I mean, I guess you see that the small peaks that you've indexed as the copper telluride peaks are disappeared.
Yes, actually in 5%, so there is few peaks, but in the label, so it will not clearly visible. But I'll show in the detail refinement in the supporting figure.
I think both A and D need to change. Okay.
Okay.
Because it doesn't really show anything. You can combine it together into a single synthesis figure, where we basically say, so you can go the carbothermal route and you get powder, but that gives you you should link it directly to the data that you get. So actually, you don't need the D here because you don't need D for this picture, right? This picture, each picture should tell a story. So the story you're saying here is that by doing carbothermal shock, I can freeze the reaction at different points, and after fixing the discontinuity, you basically show that you're able to get phase purity after inclusion of titanium. So you need to show at least the difference. This picture here is for what? For excess titanium or without?
This one.
B is for what?
B is for like how the phases evolve actually. So at different as I quench at different temperature. Reaction.
No, but where is the extra titanium added? Is this with extra titanium
No,
added?
no, no. This is without extra titanium. So
Do
actually,
you have anything with extra titanium added?
yes, okay. There is the figure C.
Okay, but then B and C are basically telling the same thing.
So like at first, so I need to see now that the phase is forming or not. Then I know that so there is few impurity phase. Then I add the titanium.
I mean, do you have the B picture with excess titanium?
No.
Yeah. Should, if that is
That would be
there.
nice, yeah.
Okay,
Because then
okay.
you show the story is complete, right? You've basically
Okay.
done this, just observe the impurity phases and then added excess titanium. So what you're going is in story, right? From B to C, you're adding excess titanium, and now what you should see is that no copper telluride should form,
Okay.
right? That's what you want to show. Anyway, it'll be useful for you, this information. You should collect that data also.
Okay. So like with excess 2% titanium, so I need to run all. Okay.
Exactly.
Yeah.
So then you have A, B, C, and that figure should be D, and then just like combine it. And this
Okay.
figure D that you have here right now, you can put in the next. I mean, you only use it if you want to do thermoelectric or some other performance, right?
So actually, initially, synthesis is for like I got like so I can directly cut, but actually the density is very low. So that's why ultimately we have to do the SPS.
I know, but the point is for this phase diagram picture, you don't need the DJS. You can do it with carbothermal, right?
Yes.
You don't need figure D. It's not central to your story.
Okay. So then actually.
Only if the transport comes, then you can use it, right? You can say for scalable synthesis, we use direct joule synthesis.
Yes.
And then because the density is low, we pelletize it using SPS, and here's the transport data.
Okay.
Otherwise, the figure D is what's the point? It doesn't serve any purpose.
Okay. No, actually, so during the synthesis, so I told about the scalability in the first. Okay, so I can tell that in later actually in the.
Yeah, you can do it at the end maybe.
Yes.
Sure. You can tie in scalability some performance. Otherwise, of course, you can say scalable, saying, hey, by the way, there is a scalable technique with rapid joule heating. We call it DJS, and you can make large size samples through this. That's fine.
Okay.
But what's the point of that? Scalable synthesis is for something, right? So at least you should have thermal conductivity data as a function of copper doping or thermoelectric data. That's what you should end with. Okay. Next figure.
So this is actually figure 2. So here actually I'm talking about these two phases. So actually at 310 Kelvin, so we saw, so there is some extra copper position is generating. And so we have like synchrotron data at different temperature. So so still 320, so there is like the rhomboidal phase is coming, and after that the cubic phase. And after like 480 Kelvin, the phase is slightly decomposed to forming few copper telluride. And here I show the Rietveld refinement of 250 and 350 Kelvin data.
I'm okay with this. I don't know if you guys want to add anything to this.
You need DSC support with this? Also, you have previously showed, right?
Yes, I have, but DSC data is not so good actually. So I have the DSC data. So that's why I just inside in the supplementary.
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 That's fine.
And
So
then
no transport data yet.
I have, but for this is not for the phase PO.
Yeah, phase PO data is not there. Okay.
One more sample after SPS.
And actually, this is the XPS data. So actually, Devi feed this curve, then I will just like plot it.
The fits are okay because Debbie and I spoke about it. I don't think you should worry about it, man. So it's good. So that bit is fine.
Then just refinement actually. That's it. So I need to collect the transport data.
Yeah, some sort of transport data, even if it's not good thermoelectric data, you should collect some transport data.
Okay.
And the band structure. That's what's missing.
Okay.
So at least like the phase pure compound versus not phase pure compound, very minimum. Then you show the transport data and then at least thermal conductivity, if not anything else, because the thermal conductivity is quite low. And then ideally we show some doping effect. That would be quite nice. And then push Andy, right? Like, do you have the band
Yes.
structure? We need to on the band structure. And then based on the band parameters, we fit the transport data that your paper is complete. Yeah. Okay. All right. Anybody else want to share anything? I have 11:45 stop, so I have 15 minutes. I have to go somewhere, lunch meeting. Okay. All right then. So let's wrap it up. Shorter meetings are better. Let's see in 2 weeks. And see most of you at the group meeting in an hour and a half. Bye-bye.
Bye bye.
Bye.